My name's Corey. I'm a junior in aerospace engineering, and I'm the president of Purdue Aerial Robotics Team. Purdue Aerial Robotics Team is a club made of over 50 interdisciplinary students, and we've spent the year building a composite airframe. Compared to last year, the airframe is similar, but there's a couple minor differences on the outside. The shape of the wings have changed a little bit, but namely the changes are on the inside of the aircraft. So the composite interior internal structures are much more lightweight, much more optimized for this year's mission profile. Every single year, PART attends the SUAS competition to build an aircraft to satisfy the mission requirements. Every year we've seen improvements on our composite airframe design, and that is the same this year. So this year we've created a large aircraft, 13-foot wingspan called Rocinante. Rocinante is a over 90% composite airframe with composite internals and external structure with a fully customized design for the mission. To perform the mission, there are many different systems that are communicating throughout the flight. The aircraft starts by taking off from the ground through a manual takeoff, and it navigates the waypoints through our custom Dubin's GNC algorithm. That is all running on a Pixhawk and flight controller on the aircraft. And then we continue into our waypoint identification section. So we do search passes over the runway. During that, we have our custom onboard software that is running on a NVIDIA Jetson. Throughout that, a GoPro is taking frames and sending them down to our custom ground control station. There's an active communication line between the aircraft and the ground station as they send data, validating targets through a manual human operator on the ground. Once those targets are identified, the GNC algorithm then predicts when the best optimal drop time is for our payloads. So those payloads are on board the aircraft and they have their own microcontrollers on board. The GNC algorithm, after computing that optimal moment, will fly the aircraft around, and at that waypoint that it's previously identified, it will initiate the drop. On board the drop payload, we have a microcontroller, and that is going to initiate the parachute deployment. That repeats 5 times, and then we land the aircraft back down with a manual operator.
For the autopilot, there's basically 3 modes that we have. It's manual mode, where essentially it's just full manual control via the pilot. Then there's stabilized mode, which auto levels the wings. So if the plane goes into like a certain bank and you release the controls, it will flatten out. And then there's fully auto mode, which flies all the waypoints autonomously. And essentially the capabilities for full auto mode is that when we upload waypoints to QGC, Crew Ground Control, the airplane should be able to fly all the waypoints on its own at a specified airspeed and altitude, and it'll maintain the pitch and angle of the aircraft such that it basically maintains that line and whatever GPS track we set.
So for this year, we have focused on using the Dubin's algorithm for navigation. So given the different set of waypoints as input, we take into account the turning radius of our aircraft as well as other constraints, and we determine what path the airplane should take to get through all of the different waypoints. In addition, we're also creating an airdrop timing algorithm. So this takes into account, the wind speed, the conditions at the day. And in addition, we also take into account drag and different kinematics of the parachute as well as the capsule. And we determine when to specifically drop each of the water bottles so they land on the plane. For our hardware, we're using a Pixhawk. We're running ArduPilot, and we'll also have it connected to a Jetson computer to run all of our different codes, our airdrop code as well as our Dubin's code. So our different codes are actually going to be combined into one module called Mega Mission, which allows us to fly the different waypoints through an initial pass through Dubin's. And once we get all of the target data from our software team and camera detection, we're able to compute when we drop each of the different water bottles. We're using ODE45 integration method, so we can calculate based on the different time steps when the appropriate time is to drop each of the water bottles. So now that we have those, we consider those waypoints in our new Dubin's algorithm that we generate. In this new Dubin's algorithm, it'll have 5 passes around each of the waypoints because you have to drop and then pass through all the waypoints. In addition to those waypoints, of course, we have the different drop sequences.
To have the payload accurately drop onto our target, we're using the coefficient of drag, wind velocity, and initial velocity of the plane to trace back to the plane and have the GPS coordinates of the drop point accurately calculated.
So for the testing we've done so far, we tested on Anaconda, the smaller foam aircraft. So far, we tested the Dubin's algorithm fully autonomously. So we took off, put the plane into autopilot, and the aircraft flew the waypoints on its own. And the entire time, we just kept the visual on the aircraft and was ready to switch back to manual mode just in case something went wrong with the autopilot. But so far, the autopilot seemed strong and flew the waypoints correctly.
This semester, we added a function of battery control. When a power rail gets below a certain voltage, we'll cut all the power rail except the connection to the autopilot computer, since that's only one system that needs to survive for emergency landing. This year, we continue to use GoPro as our camera for image detection. We considered other options for the camera system. We decided to stick with the GoPro since we know that was working. Easier for us to transmit the data using GoPro. ODLC system is object detection, localization, and classification. It's our software system to detect the target on ground from camera, transmit the data of the image, and then analyze classification.
So for our ODLC system, we use a GoPro Hero 10 Black. Videos are downloaded to Label Studio where target images are detected, localized, and classified. Afterwards, the GPS location is determined from the range and given to our GNC team.
We also have worked on improving the robustness of the powerboard by reducing the wires between our powerboard and autopilot and flight computers.
In this semester, we use IP communication over a local network to send videos and telemetry. Videos is given to our ODLC system to local targets, and telemetry is responsible to make sure the flight system is stable. We're able to maintain the connection by using the rocket antennas on the UAV and the ground station.
As for testing methods, systems integration and certain types of testing are completed locally, whereas for troubleshooting and field testing, it's done with foam planes and quadcopters outdoors, as well as to check each system and to ensure that each section works.
The criteria of success for the payload drop and failure are that the water bottle and payload must fall from 75 feet or more in the air, and it must land within a 20-foot radius of a respective circle that is specific for each payload. The fall must be safe for humans to be in the area, which we quantified this velocity to be 15 feet per second. There must be a fall arrest method present, so we decided to use a parachute for the fall arrest method. And all water must remain in the water bottle on landing. The payload and the water bottle must stay within the 20-foot radius upon landing in the circle as well.
So to release our payload from the drone, we have this dropping mechanism right here. And the way that it works, we purposely designed it so the payload would hang perpendicular to the dropping mechanism. This prevents any off-axis torque on the actual servo itself, and it also makes it a passive system instead of an active system where the servo would constantly have to be on to keep the payload up. We also chose to go with a small servo and adaptive arm instead of a larger servo to save weight in the drone. This dropping mechanism connects this servo to the flight controller with these wires right here. And GNC actually has a when to drop algorithm, which is a Monty Python algorithm that decides most optimal time of when to drop the payload to ensure and maximize the chance that it lands and remains within the 20-foot radius circle. And they also know when to drop which bottle because each bottle has a specific shape or color associated with it that has to land within that circle. If you want to come over here, we can show a test demonstration.
In my hands is this year's payload. As you can see, it's divided up into two sections, one being the electronic housing at the top, the other is the peanut butter jar, which holds our water bottle. As this is blow molded, we attach our parachute into this portion to make sure it would stay sturdy and wouldn't come out, as we will be losing points if the payload separates into multiple components. So getting into the electronics chamber, as you can see, I am holding down a limit switch, and that limit switch, when pressed, will go inside of our entire drone. When unpressed, it'll actually start a timer, which will release this mechanism you see over here. Currently, it has 0 seconds on it for testing purposes, but for our final version, it will be around 2 seconds depending on the drop. As you can see right here, once I release it, the entire parachute falls through. The way this works is that a servo actuates a small paper clip and bars over this little section over here. From the opposite end, a rubber band comes about this point and latches on to said paperclip. The payload, or rather the parachute, is wrapped around by the tensile force of that rubber band. Getting into the nitty-gritty stuff of the electronics, as you can see over here, the entire electronic chamber is hollow and is powered via a battery and an Arduino Nano. The limit switch is mounted inside of the cap and it is bolted on currently. to ensure we can replace stuff if we need to. And finally, this wire over here controls the servo and is routed from the inside of the entire cap. And as I was showing before, you can't fully unscrew this peanut butter jar to access the water bottle or any other internal contents.
So as far as testing goes, we've done some dropping of water bottles to determine what fall speed and what impact speed they are able to withstand and what speed seems to be safe for humans to be in the area. That's how we came up with that 15 feet per second number. We've also done some drop testing of our full payload from various heights to determine how long it takes the parachute to unravel so that we can then refine our aiming algorithm around that parameter. And we have determined that the delayed deployment system does work and that the parachute does deploy as intended at a later time, which will allow us to stay very accurate to our targets and allow us to stay within the required area.
Yeah, so our wing tail shapes this year were defined a lot based on last year. You know, our big decision that was different this design cycle was that we chose to keep the shape of the fuselage the same. That was for manufacturing reasons and, you know, having a starting point. But what that meant is that when we looked to our wing and tail, we could do a lot of work on sizing down the wings and adjusting it so it would be a more efficient wing that also handled the conditions of flight that we were looking at better. But the tails really did not change that much because for a, again, similar fuselage, it required a similar amount of lift and the stability hasn't changed that significantly since previous years, even with the redesigned wings. So for center mass for the aircraft, we focused around making sure that, of course, center mass ahead of the neutral point and stability, but also we were looking at where we can have our coefficient moment equal 0, or where our trim condition was, to have the most efficient possible flight. Because of course, if we have to trim the aircraft for a steady level flight, that means that that's going to incur extra drag and extra effort on the part of the pilot. To that end, we adjusted the center of mass until the plane leveled out at around 5 degrees angle of attack, which was right in between our cruise and loiter conditions. And we also made sure to place it within the payload bay so that as mechanisms designed their system, if the payloads were dropped in flight, the center of mass wouldn't dramatically change, meaning that the flight characteristics of the plane would stay approximately constant at all times.
So our composites last year were a twill weave. It was 2 layers of twill for all of our aerodynamic surfaces. This year we changed to a plane weave just due to sourcing and due to sourcing problems, but we went with just 2 layers of plane weave, and then our wing internal structures were made out of, instead of plywood like we had in previous years, it was a sandwich of balsa and a layer of plane weave on either side. With our fuselage, we had our, last year we had 2 layers of twill weave with a core material of Soric acting as a spacer, and then another layer of twill. This year we chose to switch out that Soric, which ended up absorbing a lot of resin and adding a lot of weight to our fabric, or to our fuselage skins, and we added in a layer of unidirectional weave to sort of take the longitudinal stresses of that the fuse would handle, and then we sealed both sides with some more uni to just distribute those forces and make sure to get a clean seam. Yeah, so because we changed the composites for our fuselage skins, they were less strong overall, which meant we needed to reinforce our internal structures, which meant we added in a lot more internal structures than we had had in previous years. With a lot of composites work, that obviously requires a lot of safety, so we make sure that any members that are actively working with any sort of composites, especially with power tools, are wearing full respirators and safety glasses to make sure that they are safe in that respect. And if anyone is nearby, they are at least required to have an N95 mask, if not a full respirator as well. And we try to do almost all of our composites work outside so that there's the full ventilation of the air. We also have safety glasses and gloves for any sort of power tool usage, and gloves for any sort of composites work so that the resin does not irritate students' skins.
This year, we plan on making an internal structure because we took strength out of the skins of the fuselage, and therefore we decided that we needed to have an internal structure that could stand by itself. This internal structure was built to help withstand torsional forces from the wings, as well as forces that may come from landing in the front landing gear or the back landing gear, as well as the potential for a vertical flight maneuver given the rare opportunity that occurred. To do this, we focus on a spar system, basing our design off of relatively common flight design mechanics. We decided to spread out the force between the different bulkheads of our internal structure by creating spars in between different sections. This ranged from not only from the tail and motor section to the main fuse bulkheads, but also across the fuse bulkheads to the nose bulkheads. Our idea here was that we would be able to spread out forces across the plane, and while using the skin, not rely on the skin for taking in and dealing with force. So that way the plane could stand up by itself, even if the skin had lost enough strength to where it couldn't stand by itself.
Ultimately this year, we wanted to improve consistency on landing, and we wanted to reduce weight on the landing gear. And basically for consistency, what we did and what we found out after testing for different components such as wheels and suspension systems, we found that keeping it as similar to last year as possible was the most consistent way to go. And so we basically just redesigned last year's bogie with a suspension system that could allow us to do grass landings and concentrate damage from poor landings away from the fuselage to an easier fixed landing gear.
For example, we created a new truss design at the rear of the aircraft using carbon fiber rods, and one of the calculations I worked on was determining why we should have 3 rods instead of maybe 2 rods or 4 rods. And because those rods were placed at an angle, we also needed to have truss cups that would make the rods touch the bulkheads at the right position. So that's also something I worked with my team on to